So our next speaker, so we have the privilege to have him here, is an associate professor at the University of Amsterdam, lecturer of deep learning at the a Master of Science in AI, scholar of Ellis European Network of Excellence in AI, co-founder of Ellogon AI that builds AI for immunotherapy for cancer patients.
Yeah, Mr. Gavves is already on stage, but let's have a warm applause for him. Welcome on stage.
Thanks. Hi there. Okay, it works.
The floor is yours. Thank you.
Thank you very much. Yeah, thanks a lot for the honor of having me here. And thanks all of you for attending. So today I'm going to talk about my recent work in causal machine learning for the real world. And well, there was a already introduction, so very briefly, I am an associate professor at the University of Amsterdam, working mainly with deep learning, starting grant laureate and VD laureate, Ellis scholar, and co-founder of Ellogon AI. My research interests, so I'm an academic. I mostly do research for a living, and I teach as well a bit. My research interests are on dynamical deep learning, so basically deep learning of, let's say, temporal data, spatial temporal data, with applications to robots, so robot learning, causal representation learning, and AI and science. So all these subdomains make an extended use of time, of space and time, as I will detail next. And perhaps as like a sneak peek with Ellogon, I mean, that's not going to be related to the rest of the talk, but with Ellogon, in case any of you is interested, we're building advanced computer vision algorithms for analyzing computational pathology biopsies with respect to particular biomarkers and personalizing treatments for cancer patients. Anyways, I will continue now with the main theme of my talk. So a big question right now is how smart is AI? We have, of course, the ChatGPTs, the llamas, Dino, many models. They do remarkably well in a lot of tasks. I know quite a few of the like core researchers that develop these algorithms. It's not magical. It starts working, but what does it mean? Like, what does it mean to work? What I would consider truly intelligent, or at least I would like hope for my algorithm to achieve, is some sort of behavior like what a crow would be doing. So, for instance, when I have the crow here, and then like the trainer adds a sugar cube into the tube, then the crow has to reason about the physics of the world, the fact that it cannot really fit through the tube, has to find a tool, has to remember what the tool is, how to use it, and so on and so forth. Are models like ChatGPT able to do something like that? Actually, they are not. They're not too bad. I asked exactly this question to ChatGPT. So I took a screenshot, which is, okay, not that fair. So it's not the whole video, but okay, regardless. I gave a screenshot. I put the question, you're on a bench, and I throw you like red cubes of food, of sugar, inside the transparent cylinder. What should you do if you were a crow to retrieve the cube? And give some answers. They're not bad. They're very generic. In other words, it would be very hard to give these responses to a robot and ask, like the robot to successfully get the cube. So where is AI going? In my opinion, we've been working a lot. I've been working a lot in the seeing aspect. So we're training algorithms to see very well, to understand the visual world very well. And I dare say, that is, of course, a subjective hypothesis, I dare say that we're quite close to doing it really, really well, to the extent that perhaps there's not going to be much more to be doing there, like in that direction, in a few years. So we go from seeing to interacting with reality. I think like that's where it's going to go. So we have to have now models that understand much better physics and causal, like the causal physics and causal relationships, the causalities of the world, that they have much better spatial memory and navigation capabilities. They've got the capability to reason about the world and plan, or what I would call, in short, like cyber-physical AI. So AI that connects somehow the algorithm, the data world, with the physical world, like an AI that doesn't just sit in the cloud and does what it is supposed to be doing. Now, I'm not really the only person that I'm pitching this. Fei Li, who was the creator of ImageNet, or Lacan, who's most probably like one of the most famous, like it's one of the fathers of deep learning, say very much similar things. And what does it mean, in practice? Of course, that's like a vision, a big idea, whatever. It could be also bullshit, right? Well, I think what it means, at least to me, it means that we have to have robot world models, so models, AI models, that model the entirety of the world in a grounded manner, which means have robot world models that understand the dynamic and physical priors. So for instance, Newtonian mechanics, that they know about the cause and effect relations of the world. Like what happens if I take the laptop and I close it, or if I take like an egg and I throw it? What will happen in that case? ChatGPT, Dino, all these models, they don't really have this capability. Of course, you can hack it. Of course, you can really train it specifically for particular cases. You can do if-then-elses, but that's not good enough. That's not AI. So we want to have this automatically. We want to have this learned autonomously. So we have to have the causal inductive bias, how I can interact with the world. What does it mean to have a box? What kind of uses does it have? How can I exploit this to reason about the world? And also to answer perhaps counterfactuals, like counterfactual questions or hypothetical questions, what ifs, basically, right? Like, what if I don't mop the floor, which is now wet? Of course, like, as a robot, that's like very important, right? Because if you are a cleaning robot and you don't do that, perhaps accidents will happen. Besides that, we also need embodied inductive biases. So we need the algorithms to understand more about what it means like to be oneself in the physical world. And all this has to be in an open world. If anything, ChatGPT, one of the biggest successes of ChatGPT is not accuracy. I've been doing AI since 2008 when I started my PhD. And, well, we always had high accuracies, right? Because an accuracy is just a function of how complicated and how difficult the data set is. If you make it super easy, then you're also going to get 99% accuracy. The good thing about ChatGPT is not that it's accurate. The good thing about the ChatGPT is that hundreds of millions of people used it and keep using it, and it doesn't break. It works really well. Does it work perfectly? No. Does it say stupid things? Definitely. It doesn't matter. It doesn't break. It works really well. I mean, it's only going to get better from here on. So we need an open world. Like, that's how ChatGPT made it. It was like made, left out in the public. With, like, basically, they used internet-level data. They scraped the whole internet, literally, and that's how they did it. And we have to do this with what I envision to be AI operating systems. So, like, that's a provocative, perhaps, thought. But in my opinion, right now we've got I'm not a software engineer. I studied like electrical and computer engineering, but I never really went down, so I'm not super expert on this. But as far as I know, an operating system is basically a software framework that orchestrates things, that like guides the operations, that retrieves, that calls functions, and so on and so forth. So what happens in our future systems when all these libraries are not deterministic anymore? Because AI is not deterministic. AI is not deterministic because the world is not deterministic. Like, my computer vision will never give me always the same outputs. Like, just small changes will create different outputs. How am I going to have AI that actually, an operating system that manages to, integrate all this information and all these tools and so forth? I think we will be seeing AI operating systems something like an LLM, like a ChatGPT can be an operating system that basically drives the operations and the functions of our computers. In fact, this is already sort of happening. So like ChatGPT starts implementing tooling. It's actually one of the biggest, well, Sam Altman says that's like the biggest, let's say, use case for ChatGPT, and I agree. Like, if anything, this is what, where it's going to thrive. And I think, for operating system, that will be a cool thing to, to have. And okay, this is how I think it should be done. I will present you a bit quickly some of my works that go in this direction, and a couple of works that go a bit like sideways, in case anyone is interested. So this work is called Dream to Manipulate, and it addresses compositional manipulation world models. So basically, AI models that model the entirety of the world. Well, in this case, the entirety of the world being the surroundings of this fixed arm robot. And it was work done with Leonardo Barcelona, Andrei Zadainchuk, David Allegro, Samuel Papa, and Stefano Guidoni. Very quickly and briefly, what is our overall pipeline? We start from the real world. Like we start from like I would like to have a model that works with a real robot, not just like a synthetic simulation. So how do I? Oh. How do I get there? I've got my real scenario, and what we do is we basically detect all the objects in an agnostic way, in an object-centric way. We detect all the objects from a series of videos and frames. We dissect them, we segment them out, and then we use Gaussian splatting to reconstruct them. I'm going to explain in a bit more detail, step by step, the process. Now I'm just giving a big picture preview. So we got the object scattering Gaussian splatting that basically represents in 3D my objects. Then I pass them via through a physics simulator. Until recently, physics simulations were reserved for basically generic environments like computer game environments. This is like my environment. It's like this robot's environment. So we're using it actually to model, to simulate physics of my world. How do we do that? We pass as input. Now you can consider the physics simulation as a function. So we use as input to this function the object-centric Gaussian splatting. So we put basically all the objects, the 3D objects, in my physics simulation. Of course, this is done in a generic way. We don't really say the robot exactly what it should be seeing. Of course, you can do these things much simpler if you make assumptions about the world and about the objects and whatnot. This is done in a generic way. And we use the physics simulation to basically update the physical parameters of my world. The position of the objects, the rotations, the angles, the speeds, the velocities, the frictions, and everything. Now, by having this physics simulation, what does this allow me to do is that I can actually work in imagination space. So my world model can now imagine worlds that never existed. In this case, world is the parameters of the robot, right? Like the robot arm, where it is, where it moves, how it moves, the different objects, how they are situated in the world out there, and whatnot. So we can play out imagined worlds, and this is actually very useful, as I will see. Now, what does the Gaussian splatting is? Do you know Gaussian splatting? No. Right. So Gaussian splatting, you can think of it as sparse 3D pixels. So pixels, 2D pixels, is basically a dense array of values, right? Like if you actually read your JPEG, it's a matrix, it's a table of numbers. You can think of Gaussian splatting like as a point cloud, where each point is a Gaussian, the Gaussian being an XYZ like blob, together with some colors and whatnot. And then if you want to basically reconstruct your 3D scene in front of you, you simply need to integrate basically the Gaussians that fall along the ray that connects your point of view with the particular perspective that you want to see, to render, basically. So basically it's a graphics method, originally proposed by a fellow Greek, Dretakis in India, and it has taken the world by storm. It's actually one of the most, it has been published 1.5 years ago, and there are like hundreds, thousands of papers actually, an algorithm. So you can think like that most probably the next Google Maps will be if not already, they will be implementing this kind of algorithms for rendering the 3D photorealistic like buildings and whatnot, the worlds. It's really popular because it allows for real-time rendering, high-quality renderings, good depth rendering, fast training, and explicitly grounded representation. That's like the last point is actually what is important for us. And to give you an example to understand how, let me see if I can open my hotspot. So this is not demo from me, of course, but it doesn't matter. No, that's quite slow. Before it was faster. Well, it's going to take a while, so before it was... Oh, never mind. When it loads, I'll show it after. Anyways, you can think of it as giving really extremely photorealistic results. Basically, you can use it to render your 3D scenes in real time very accurately. What do we do with it? So we use grounded sum, segment anything models. So segment anything model is something like, it's called the foundation model, which basically receives as input an image, and then you can use it to segment any object that you would like based on the prompt. So I say, for instance, like segment for me all the objects, or the red objects, or the tables, or armchairs, and does exactly that. So we do that to segment all the relevant objects in my world, and group it across views, because my video is a stack of frames, right? So I have to somehow link all these frames, all the objects per frame. And then we integrate it with explicit physics engine. So here is a demo with a synthetic environment, synthetic world. So basically we have recorded, well, it was not us in this case. We already had the video. We have like the table. We use Gauss Splatting to 3D reconstruct the world, and we can dissect and start manipulating with our physics engines the objects. We can like take them, throw them around, whatever we want. In this case, we use PyBullet, and PyBullet require meshes, so mesh grids. So we have to convert the Gaussians, which are basically independent blobs, into these meshes, and then it works. Like this, what we are able to do is basically reimagine, reconstruct past trajectories, so we can use our robots to, like, our robot memories, let's say, to reconstruct them in this virtual space. But more importantly, we can imagine new ones. So I don't know, I guess you've seen The Matrix, where Neo has like this like library of weapons, and then you got like all sorts of like skills that they're learning. So it's something like that. So basically, because we have a sort of personalized digital twin of my world, I can use it. I can use the photorealistic reconstructions to play out any type of trajectories or experiences we want. We can use it for one-shot imitation learning. So imitation learning is, let's say, one of the most popular supervised learning paradigms now for robotics. Basically, you manually instruct the robot to do something, like, for instance, grasp an object. Like, for instance, how would you teach a robot to pick up a bottle? You can start like to instruct explicitly all the fingers and all the locations. I mean, but that doesn't work. That's not very robust. You can use supervised learning with deep networks and collect first a lot of data of like somebody, for instance, like that wears a glove, how they hold the bottle, and then use supervised learning to teach the robot to do exactly the same. So this is called imitation learning, and as with all supervised learning like solutions, usually it requires lots of data to do it accurately. In this case, we show that you can actually use it for one shot. So with a single example, we can teach the robot to perform the tasks that we ask from it. And it works even in a real robot. So this is what Leonardo has programmed. The robot saw just once, like an example of what means like I pick up a block and then I put it in the bucket, and then it was managed to succeed in like performing this task pretty accurately. We have doubled the accuracies, and most importantly, it worked really well for the so-called out-of-distribution cases, when my objects don't really look like my training data. So it does pretty good in extrapolation and generalization. Beyond physics, however, dynamics, I mean, the dynamics of the world are not all physical, right? Like we've got, of course, the physical dynamics of, for instance, if I take a bottle and I throw it, what will happen? And this is basically what we model here. But you also have the causal dynamics of the world. For instance, if I take the water bottle and I throw it on the laptop, what will happen? Like probably the laptop will stop working. How do you teach this kind of like knowledge? How do you put it into your like algorithm? And you can think of this as an inverse graphics problem. So for instance, it's like one of the most popular paradigms in this is causal representation learning, where if you have, for instance, the image, you want to decompose the image into these vectors, these factors of variation, that basically, if you had them, you could resynthesize them. You can resynthesize the image from scratch, like it's an analysis by synthesis paradigm. In these works, we say that for causality, it's very important to use time. So, well, with time, you actually understand much better what are the actions and the consequences of the world. And you can use it to answer questions like, what are the causal variables of the environment? So what are the causal environments on this like simulated, like synthetic, like screenshot, like the buttons of the oven? Like if I press the button, something will happen, fire will pop up. Or if I throw the egg on the oven, on the frying pan, when there is fire, then the egg will be cooked. I would like my algorithm, my robot, to be able to learn that automatically without me telling exactly what it should learn. And I want that because I cannot have all the million if-then else's in the real world. Well, of course, this is not really real world, but we're getting there. And in this model, we have a spatial temporal directed cyclic graph, which is connected over time with the robot variables and the interactions, but I'm not going to bore you too much with the technical details. The interesting thing here is that we managed to recover, to obtain our objects and our interactions completely automatically from our videos and from our images. So in a way, our algorithms can start now understanding what are the consequences of their actions. You can use that afterwards for probabilistic inference. You can ask questions, okay, what would happen if, I take the bottle and I throw it on the glass, without having to have explicit data in your training set to learn this kind of questions. Now, on a perhaps more, how would I say, like timely topic, I will discuss a bit more on my recent work, unpublished, on code generation for electronic design automation. I don't know if people here work with like designing electronic or electronic boards, but well, if you do, like this may be relevant. So what we do here is we're proposing a from CAD to LAD approach, like learning, instead of having computer-aided design, learning-aided design. The idea here is that coding is a universal language in engineering, which is both understood by humans and machines. So code is actually a language. It's literally a language that both I can understand and the computer can understand. So what we can do is we can use it with electronic design, numerical simulation, computational engineering software, and so forth. And in fact, we can use it with LLMs to learn to code. We use it with LLMs. LLMs have already started started to learn to code extremely well. Now most of my PhD students use it like all the time. Of course, there's Copilot and all sorts of other tools. Again, not perfect. They're not like solving the whole thing, the whole chain, but the progress is really, really fast. And I do know people that work, for instance, in Meta. They really throw a lot of money for like this kind of problems. So what do we do in this case? We have an LLM which receives the file specs, basically what exactly electronic board would we like to have in the end, together with some task-related examples. So we basically use the experience of expert engineers that have already developed things. So this is like up there, like in the top. And we combine them. Then we use three, again, types of LLMs. Well, basically the same LLM, we just use a different prompt. One for basically determining the geometry of your solution. Another LLM that specializes on returning the brute force or the Bayesian optimization parameters that we're going to use next. And then one LLM to inform about the constraints that we want. For instance, that particular materials should not like touch each other, or that we have particular geometries that we want to have to respect. So once we have that, then we can pass it to our simulator, like ANSYS. And further, we can also combine it with brute force optimization or Bayesian optimization, so that like we try a solution, we see how good it is, and then we inform, like we create a feedback loop, and we inform again like our system, our framework, with new, better parameters. And if you do it like a few times, then you start actually getting better and better quite quickly. So this is more or less the prompt. That's called prompt engineering. Like up there is the prompt, and below is the answer that the LLM, the ChatGPT, returned. So here you have got to say, like in the PCB setup, a taper with 2 steps is used for the impedance adjustment. Now the code should be adjusted to 3 steps. Answer the following question: which sections in the parameter file and code file describe the taper? Which parameters have to be added? Which code sections? Which geometry? So this basically it's the so-called chain of thought paradigm, where you have to basically explain to the LLM the steps that you would like to follow in the reasoning process so that it answers correctly. And by doing that, like by giving like, these explicit instructions, it can spell out quite accurately the parameters that you would like to have in the system, and to generate the code that the simulator afterwards can run. So these are some examples of what we designed. So this was basically with, we used it in a in a real company with real designs. These are the 3 designs we obtain. They are actually pretty accurate, and these are the, let's say, the RF curves that we obtained, which are close to the desired specifications. Next work is, again, on another timely topic, AI-generated images. So one of the biggest problems nowadays is, of course, at least my mom doesn't really I don't know if that picture is from like a real person or a real village or whatever, like it's too pretty, and they start building their own internal tools, right? Of course, AI generation can be quite dangerous in reality, because you cannot really trust what you see. So it would be important, it is important to be able to detect generated material. And in this work, we basically rely on some frequency decompositions. I'm not going to bore you with the technical details here, but we rely on technical frequency-based decomposition of the image signal, and are able actually to obtain state-of-the-art results. For instance, the algorithm was able to detect that this is a synthetic image. The red warrior has actually 6 fingers. It has spotted this information. Or that that picture is also a generate image because, well, whatever, it's focused on mostly on very dense, very too detailed, too artistic regions in the image. Interestingly, these R algorithm, as well as other algorithms, can be easily hacked. So if you take synthetic image, like, so this is probably you know it, it's the Pope with whatever, Balenciaga, like clothes or whatever. It was a fake image, like, that they put like last year, I think. Now, like if you feed the image directly, the algorithm can very successfully detect that it's a fake image. However, if you take a screenshot with your camera, with your phone, and then you upload that one, basically your camera distorts the frequency fingerprint that our method uses to detect that it's a fake. And the same for other methods, like all actually pretty much suck. So this is actually a risk for AI-generated images and their detection. And last, another work that we do in parallel on machine learning. So for those of you that are interested, for instance, there's like GDPR or like privacy settings and whatnot. Well, there are machine learning and methods that basically can very targetedly remove sensitive information from your machine learning models, your AI models, without having to retrain them from scratch. And I don't know if that's like my plus questions or minus questions, but I'm done. So my conclusion is that causality and physics are super important. They're not just needed because they're they're nice and interpretable, but they're very useful to improve our machine learning models, to make them make models understand better reality, and especially towards cyber-physical AI in the real world. I think it's a super exciting direction. Yeah, thank you very much. If you're interested in any of this, please let me know. I'm also open to discuss for collaborations or whatever, like if you're interested in this space. Thank you.
That was very interesting. Let's see if we have any interesting questions. Do you want to take the first one, Despina?
Yes. So, I know you can read. I'm going to read it for you. In what ways do you think robot self-awareness could transform interaction and collaboration between humans and robots?
Well, I think in a profound way. I mean, first of all, I don't believe that. I think it's cool to watch Terminator, but I don't think it's that like easy or obvious. I don't think that there will be sentient in that sense. However, self-awareness is actually one of the biggest, I think, problems right now. Because like we actually have robots that work really well. In factories, robots work really well. Where they don't work is when they're close to humans. And why they don't work well? Because they don't have any self-awareness. They don't really know that they are that they're robots, right? Like they don't know the human is a human. Of course, you can, like, red team everything, like make sure that everything is safe. But until then, like until you actually have a proper solution, not if then else's, but the general solution that can be learned, I think, like then, of course, it will really change the way, yeah.
Yeah, but we're a long way until
yes.
this.
Yes. Yeah, believe me, we are.
Yeah.
Do we have time for another question?
Yes.
Yeah, let's take the second one. In the long term, how do you think grounding in reality will change the way robots interact with complex, unpredictable environments?
So for me, I'm thinking this in terms of like more practical, like, okay, we've got the Roombas. It's a bit stupid, right? You only have it because it does, like, I heard like a nice quote recently that it works 70% of the time, but it's like, that's already good enough if it's like about cleaning your house, right? And it's also safe, you're not afraid, whatever, like it saves you a lot of time. Now, when you actually have a real robot in the house, like let's say you got like Elon Musk, right? Like has figure AI. Well, it's not a real robot, it's basically humans dressed up, but anyways, let's say he managed to make it. Would you trust that next to your kid? I wouldn't. Because, like, to me, they're not interpretable. Like, their actions are not interpretable. Like, for me, so it doesn't, I don't want interpretability when I've got, like, image classification. I don't think humans can interpret their own, like, decisions. Like, if I ask any of you from here, okay, why is, like, that a laptop? you will come up with a definition that actually doesn't really make much sense if you really go too deep into that, right? But when it comes to taking actions, interpretability is very important, and I think grounding in reality will give us that. Like, it will give us the interpretability that we require, which will be very important for trusting the robots. I think in the long term, we will be able to trust the robots only when they are grounded in reality, and like that we can control them.
Yeah, that makes sense. Okay,
No.
I don't
Okay.
think we have time for additional questions, so thanks a
Okay.
lot again. This was very insightful.
Yeah.
Thank you very much.
So if anyone has any other question, you can catch. You're going to be here in the after party.
Yeah, I'll be
So
around.
he's okay. We're going to have him in the after party, so you can catch him and you can ask him whatever you want. Because I bet there's a lot of questions and conversations that we can do with our speaker.